Hey, what's up, guys? Okay, so today I want to start with the proof. Talking about a very difficult theorem, or Toda theorem. And in order to prove this, that we first need a Valiant-Vazirani theorem. So that's called VV. So Valiant-Vazirani theorem. So we need to start from this, and we can prove the famous results called the Toda theorem. And then there's a Toda theorem 1 and 2. Okay, so these are basically the I think this won the Turing Awards. So uh, the first total theorem is the PH is and the BVP to the parity P. And there's a de-randomized version that proves PH is a subset of P to the sharp P. And the Valiant theorem basically say that if you NP, right, any set formula can be RP reduced to onset. So simply speaking, the NP is a subset of RP with the unique set oracle. Okay, so this is a unique set. So I will describe the detail in the following maybe 3 or 4 videos, but the idea is this. And the unique set basically is the promise problem that set has only like either one satisfiable assignment or no satisfiable assignment. And then so you can decide this using a parity P. Okay, so parity P is basically you can imagine that this is oracle. Basically, you can solve. So this oracle will tell you that either set formula has even or odd number solution, and so it's also BPP to a parity P. So you can imagine that Toda theorem prove one side of this particular case, just NP is a subset of BPP to a parity P, and then you can use also some tool that you can generalize this to be this. And you can de-randomize to prove this. So these 3 are the following theorem, are basically all the ingredients that we need. I mean, I will prove in the future, like 4 or 5 videos. By the way, hope you guys subscribe to my channel. And after I finish all these complexity results, I will go back to some mathematics. Okay, just for fun. If you want to see more interesting stuff, you can go to my channel. Okay, so this video is very simple. Just introduce the first ingredient. So this video I will just introduce the randomized algorithm, randomized polynomial time RP. So this is a complexity class. Basically it's very simple. Says that okay, so L belongs to RP. Satisfy if X belongs to L. L belongs to RP. Basically, there is a polynomial training machine. XR. So X is the input and R is the random bit. By the way, the random bit. So M runs in polynomial time. So polynomial time training machine M, and R is a random bit. So R at most like size of poly N. Okay, X belongs to L. Then the probability of R is a random bit. M of XR output 1 is greater than half. If X do not belong to L, the probability of random bit R. So the probability of your randomized algorithm output 1 is exactly 0. Well, so basically this algorithm only one size error, right? So just it's very powerful that it's very restricted that if X do not belong to L, the probability always say no. Okay. Okay, so very simple. And so we want to say, okay, so notice that if you compare it to the BVP, right? If you compare it to the BVP, this is the 2/3, this is 1/3. Okay, so immediately it's not immediately, but you prove that you can see these sides that BVP is like more broad version, right? Because the BVP only requires less than 1/3, but RP is only 0. Okay, so actually the simple fact is RP is a subset of BVP, and for this part it's trivial. So we need to show this part. We need to show that I can amplify this half to be greater than 2/3. But it's very simple. I just do twice. Right? I just do twice because if X belongs to L, then I do twice. Then the I will get I will get 3 divided by 4 probability, right? Because if x belongs to L, then if x do not belong to L, then always 0, right? So I just run this algorithm twice, and if any results of 1, then that means x belongs to L. Okay, so this you run twice, then you prove that RP is a subset of BPP. Okay, so now we have explained RP here, and right, and I want to also say something. Basically, is RP is a subset of NP. Okay, reason also very simple, right? What's the reason, right? So in the NP basically say that if x belongs to L, right, should be a polynomial. So there's a Turing machine M. If x belongs to L, then there will be certificates, and these certificates polysize such as M of x, y long output 1. And if x belongs to L, then it do not belong to L, then for all the certificates, for all particular length size of certificates, then M of x, y always output 0. Okay, so notice that this y need to be the same length, some particular length. Okay, so you do this kind of like observation, right? One output 1, one output 0. So obviously you just take these random bits as a certificate, right? So take this to be certificate. Right, and obviously that in the RP that you only require greater than half, but in NP you require it must be 1, right? So RP is more general version, right? So NP is more, so NP is that, right? So RP is also must be subset of NP, because that in NP that you only require 1 certificate, right? So in RP that since you're already greater than x3 divided by 4, right? So there is always a particular R certificate such that accept 1. And then if x belongs to L, do not belong to L, then all the certificates for particular length will give you 0. Okay, so simply speaking, you just use this random bit, random bit string as certificate. So easily prove that right. So you just have y to be R. So prove this. Okay, so summary. So summary is basically summary is basically right. So P is RP, right? BPP, and also subset of PP, and RP is also NP, and obviously the NP is also subset of PP. If you haven't seen this, you can check out my previous video. But this proof is simple, right? You start from set, and then you can like randomly flip coin, or randomly flip coin, and or randomly pick one assignment, and then put and check whether that assignment is true or not, and output with the half with some very small probability, and you will prove that NP is subset of PP. So PP is if x belongs to L, the probability then M of x R output 1 is greater than half. In x do not belongs to L, then probability of mx R output 0, output 1, sorry, output 1 is less, exactly less or equal to half. Okay, so in this case that you don't have the arrow amplification, but yeah. Okay, so now we have the defined RP. Okay, so next video that I will give this this proof, and then maybe I think I'll go very simple to prove this, up to here. Okay, so next video I'll prove the William-Bazzanoni theorem. See you guys next videos.